So I would like that in about 5 minutes or so, or at least at the end of the lecture, everybody understands this and knows how to do this. Why actually? Well, because inductors and capacitors, here's an inductor, right, are of course useful circuits, and we'll design interesting stuff with that. And you can't understand that interesting stuff if you cannot even, if you don't understand the simple stuff here, right? So that's why this is supposed to be rather simple, but I want to be sure that we start from a good basis. So I'll give you another couple of minutes or so, and then if you have questions, you can also raise your hand, and the TAs or I will come and help you. So you know the formula for the capacitor?
It's the same. They're just reversed.
Yeah, exactly.
The
So
current for capacitor
yeah.
is the voltage
So
for the inductor.
yes. So but the capacitor. So again, the way I remember it is it's how much charge does it store? What's the charge on a capacitor?
The voltage times the capacitor.
Exactly. Why don't you write this down? Okay, so now if we know the charge, we would like to know the current. What do we do? Okay, and now we have to do for the inductor, we have to do the opposite. V equals L. L. Yeah, that would be. There you go. You know it. So you don't need a cheat sheet. You done? Yeah. Yeah, that's right. Okay, so anybody got the who got the answer? Oh, come on, it's not just two people. This is depressing, you know. No, I really mean it that please engage. Hey, if you don't want to participate, then stay in your bed. It's a lot more comfortable than sitting around here and waiting. So who got the answer? Okay, so half a dozen people or so. All right, what actually is the answer? Okay, so let's go and look at it. So we have a voltage source, and across that voltage source we have connected an inductor. What's the voltage across that inductor? V1. Why is it V1? Yeah. If I put a resistor there, the voltage would be V1. If I put an open circuit there, the voltage would be V1. I could put anything there except maybe a short circuit. Okay? So this one's trivial. Even though there is an inductor there, it doesn't change our basic circuit understanding. Okay, so now we want to know something about the current. What do we need to know? If this was a resistor, what would we start with? What would we start with? What would we write down now? Ohm's law, exactly. Of course, Ohm's law, right? So what's the Ohm's law? It's not called Ohm's law, but what's Ohm's law for a capacitor? The voltage across the capacitor is in the inductor is equal to the inductance times di current through the inductor dt. Okay? So now, in this case, we know. Do we know this? Of course we do. It's V1, right? This is V1. Do we know this? Well, yeah, it's given. It's 1 Henry. Made a simple number. Pretty big thing, but okay. So we can figure out what this is. Is it 0? Well, no, of course not. Okay, so DIL, which is equal I1 here, DT is equal to VL, which is V1 here, divided by L1. Okay? And so that is equal to, what is VL, V1? So that's 1 volt divided by 1 Henry. So that will be 1 amp per second. So it's going to look like this. The rate is 1 amp per second. And consequently, if we wait for 1 second, we get what current? 1 amp, right? So this is high school now. All right? Simple first order differential equation. We just have to use it. It's like Ohm's law. Okay? Yes?
Since like the second one, I cannot go to infinity or anything like, does it make sense to say that the maximum current is going to be voltage source divided by voltage, a voltage source divided by resistance of inductors?
That's right. That's right. This is a simple example. You couldn't build this like this. You're absolutely right. In practice, the current would not continue to increase indefinitely, would flatten out. And you flatten out, where it flattens out is set by the series resistance R. But I didn't put anyone in, and so this simple example, the current would increase indefinitely. Okay? So we'll afterwards look at real circuits where the current is not going to increase indefinitely, but this thing is part of that circuit. Actually, it's part of lab 5. Okay, this very simple thing, and it just put with a few other things, and then basically we are waiting for the current to increase for a little while, like a few microseconds, and then we say now current do something else, right? But of course, this is an element in there. Yes.
Next slide, variable manipulation. On the next slide, you have 2 V1s and they're different.
Okay. Okay.
Can you explain once more why the voltage stays the same?
Why the voltage stays the same? Well, if we were to... so what's the voltage between these two terminals? Is there any chance it will be anything else ever? No. Okay? So what would be this other... Let's call this Vx just... or VL, actually, would be more reasonable. VL. Okay. So now we could, of course, draw KVL, right?
What happens if you have a short circuit? Then you have V1 on one side and then short circuit on the other side.
If you replace L1 with a short circuit, well, yeah, then you have something mathematically impossible, right? It's not possible to have a circuit where the voltage is simultaneously 1 volt and 0 volt. It's impossible, right? 1 and 0 are two different numbers. They're not equal. You can't make... It's something that I haven't made here, right?
But isn't that will happen after a certain time, after the maximum current starts going through the...
Okay, yes, in this, you're absolutely right. You can build this circuit in the lab, and it will... Exactly this will happen for some time, a few seconds, and then the current gets so hot that the wire gets glowing red, right? And then the wire evaporates and the whole thing stops, okay? It's true. If you put this in the lab and you wait forever, something's going to happen that makes this current not go to infinity, okay? Right? If you set the compliance on your source, on your lab source, to 100 milliamps, then it will go up here to 100 milliamps, and then it will stop because the source refuses to deliver anything more than 100 milliamps. This is not this circuit, just like this, is not what we want to build. Okay? But soon we will look at a circuit which uses this concept, but it will let the current increase for a short while, a few microseconds, which is long for circuits, electronics, right? It's short for us, but long for circuits. And then afterwards it does something different. It makes the current decrease again. So the current will not increase indefinitely. Okay? But if I show you that example to start, then I fear that the same thing happens that happened on Monday, that there is one or maybe two people who follow and the rest have a nap. And we don't need to do that. You don't need that, and I don't need that. Okay? So that's why I made here a very simple example. It's not what we're going to build, but something that we simply can understand. Okay. Are there any more questions about that? So what I would like now, what I would like now is that you really understand that. If you have a question, then please ask it. Okay? Right? Okay, so now I have another question. Just keeps going. So now it's a little bit more complicated, right? So if you look at this circuit here, when the switch is in the left position, what do we have? Exactly this, right? So apparently we are building this up little by little. Sometimes a good idea, right? So, and yes, you're right, this one should be another, let's call this VL. And then what we want to plot here is VL, all right? And these are all VLs. Okay? All right, so I'll give you again a few minutes. Please think about it. If you have questions, raise your hand, ask your neighbor, ask me, ask a TA, but please figure it out and understand it. Otherwise, we're wasting our time, right? Okay, so till
without switching that switch, the voltage across the resistor is just
well, what's the current in the inductor before we flip the switch?
So you're saying charge up the inductor and then flip the switch?
Yeah, that's what's happening here, right? We start from 0, then we rev it up. If you want, it's like a flywheel. Start spinning.
Oh, okay.
Will that flywheel just stop?
Right.
I doubt it, right?
Right, I missed the
Yeah.
Okay,
Yes.
got it.
You probably will be helped by getting a piece of paper out and drawing this. Yes.
If it's in the left position, how can we leave it? Isn't this what you just said? So, I mean, we're assuming there's no breakdown when you say long
We leave it in the position on the left side for T1. Time T1 is 10 microseconds.
Oh,
So for 10 microseconds, we leave it there. The current goes from 0 to some bigger value, but not to infinity, right? So it addresses just this problem that one of you pointed out that, heck, right? So by now you should know what the inductor current is at time t1. Yes.
Is T1 after we switch to low right?
T1 is just the time when we flip the switch, right? So there is a T1, actually I should have explained that. The T1 minus is just before we flip the switch, a femtosecond before, and T1 plus is a femtosecond after.
Okay, so before.
Yeah. So,
Right. Realistically, a circuit would have enough inductance to require a little bit of
okay, so let's maybe solve the first part of this, and then I'll give you a little bit more time to grapple with the second part. So here there is a switch now, and the switch can be in the left position or the switch can be in the right position. When the switch is in the left position, do you recognize the circuit? How do you, those who do not recognize it, how would you do that? How would you understand the circuit, what it is? Okay? So what I recommend in such a case is that we are now concerned just with when the switch is in the left position. We don't need all of this circuit. This is too complicated for just considering when the switch is in the left position. So I redraw the circuit, and I actually really do that when I solve these problems. L1 and V1. What did I do? Well, I replaced the switch, which is in the left position, that part with the short circuit. The open circuit part, heck, I really don't need that. And because now the resistor is open circuited, well, that resistor really doesn't do anything, so I leave it away from the diagram. And now I say, wow, gosh, that's exactly this, right? So we can figure out now, for example, what the current is at time t1. Actually, what will the current look like? I didn't ask you to plot it here, but that was sort of a thing. That's the same thing, going to be the same thing in the exam. And of course, once you are a circuit designer, so that will be the same thing. No, there will be not a plot there that you have to somehow fill it in. You will have to figure out what to plot in order so that you can understand the circuit. So do that. So the current through the inductor as a function of time, how this going to look like? It's going to increase like this. And what is di? dt? That's the voltage divided by the inductance, and that's here equal to 5,000 amps per second. Right? Okay. So the inductor is smaller, so the current ramps faster. So after time t1, what is the current? Okay, you can figure exactly 50 milliamps. Okay, so everybody should be able to do this. Okay, so if you have a question about that, then please ask me. Okay. All right. So now we already know that. We know that the current. We know that the current at this time, the current in the inductor is equal to 50 milliamps. Okay, that's just before we flip the switch. So now think a little bit. What happens when we flip the switch? No, I don't want the answer again from two people. It doesn't do me. Yeah.
The same current is flowing, but it's going through that resistor, so the voltage is going to change.
Okay, so the current before here was 50 milliamps, right? And now what is the circuit? Well, I really could get rid of this stuff. I think I can do this. Okay. That's the circuit I have now, okay? What's going to happen to the current? Why? Yeah, an inductor always does this, and we can just remember that, or we can see this from the equation, right? An inductor, the voltage across the inductor is the inductance times di dt. If the current was changing abruptly, what would the IDT be? Infinite, right? Infinite, and consequently would get an infinite voltage. Well, there is nothing that we would have to have an infinite current flowing through the resistor R1 in order to get an infinite voltage, and where would that infinite current come from? Right? So it's absurd. So that cannot possibly be. Yes, it's absolutely correct. The current cannot change a little bit, any little bit. And the way I indicated that here is that I have this T1 minus and the T1 plus. That's just a femtosecond before I open the switch, and then a femtosecond after I do that, after I open it. Okay, so what is the voltage actually across our inductor just before I open the switch? Okay. And just when I flip the switch now, so actually it's not 50, but almost. So how do we figure that out? Where is that current flowing? What's the current flowing through the resistor? 50 milliamps. Now we have Ohm's law, 50 milliamps times 1 k ohm. It's 50 volts, right? So the voltage, this voltage here is 50 volts. Okay, and so the voltage is actually minus 50 volts. So apparently the voltage goes, the voltage is negative, is positive first, and then it jumps.
The voltage you're measuring right there would be 0 before I flip the switch, because that resistor is open circuit.
Okay, fair enough. Yeah. So the main point that I'm trying to make here is that the voltage just after I flip the switch is 50 volts, or actually here minus 50 volts. Okay, it's much higher than the voltage was before. Okay, and even if the source had only actually here the source has only 5 volts, we can make 50 volts no problem using that inductor. Huh? It's quite interesting. So there ought to be some use for this. And then what's going to happen to the voltage across the inductor eventually? It's going to 0. Why? Well, because all the power that is stored in the inductor, or the energy, is dissipated, right, in the resistor R1. And consequently, the voltage is going to somehow decrease exponentially. I mean, we can calculate that now. We can solve the differential equation, but it's even more interesting to understand what's happening here. Okay, so that's how we solve this. And yeah, are there any questions still on how to solve this? Oops, these were too many more flips than I wanted. Yeah, no questions. Okay, you understand that? Yes?
Wait, I got a little confused. So is what we solved here the voltage across the inductor, or is
the voltage? Well, it's the same, right? The voltage across the inductor and the here it's indicated the voltage across the resistor, and so your colleague was right that then that voltage is actually 0. Okay, and
so the 1 back to 14
yeah, there is no current flowing through the. It's not very important. Yeah. Yes. So should what be 0?
The voltage across the inductor before it's switched.
No. Don't do that, right? I've told you that inductors are made out of wire. Okay. Resistors are also made out of wire. If you think about it, right? If you want to make a resistor, you just make a thin and long wire. Okay. So then you don't replace that wire categorically with a short circuit. So same thing. This inductor. It's an inductor. It's not a wire. It may be made out of wire, but it's an inductor and it behaves differently, okay, than an ideal wire.
So what is the voltage across the inductor before the switch?
Before we switch it? Well, I need to erase now everything in order to. What is the voltage across the inductor? Well, it's V1, right? Okay? Because we simply connect the voltage source V1 to the inductor. Right? Right? So same as before. All right. So that's what's happening here. If later questions come up, please ask them. Go to the office hours. Ask somebody about it. I would like you to understand that. Okay. Here now is a little bit of one more question. What's the total energy delivered by the source V1? Okay. How would we figure that out? How would you do that? What formula? Okay, what is I? L we know that's given here. What is I? At which? At T1, right? That is the total. That is the total energy. Once after T1, does the source still deliver any energy to this circuit? No. Okay, so yes, we could figure out the total energy is just that's the current at T1 here. That was, I think it was 50 milliamps or something like that, right? And then we can use the equation 1/2 L1 I square to get that energy. Where does this energy go? All of it goes into the resistor. Now, if the resistor is the load, okay, so if this was, for example, a power brick, then the resistor was the load, right? Your cell phone, or so that you're trying to operate or charge with this thing. Then all of the energy would be going to that load. Is that a good thing? Why? Exactly, there is no loss, right? That's what we want from a circuit. Remember, early on, we looked at, we have some high voltage, and we want to, we want to drop it for some circuit. Let's say we have 110 volts. We want to drop it to 10 volts or so in order to power a circuit without blowing up or so. How did you do that? Well, with a voltage divider. Was that thing also efficient? Well, hell no, right? It dissipated most of the power and very little went to the load. So if you use instead inductors, the picture is quite different. The efficiency of this circuit would be 100%, right? There is no loss except in the load, and of course that was the point of the thing, to deliver it there. Then is the load efficient? Well, that's a different story. Okay, so when we want to make bricks or so to charge our devices, then we want to probably use inductors and not voltage dividers. Yes.
When we did that with capacitors, though, didn't we lose exactly half the energy regardless of the?
That's right. With capacitors, you would want to have a current source. With an inductor, right, normally we have voltage sources to power our things, right? Batteries are voltage sources, the power outlet is a voltage source, and so on. And then it turns out you want to use an inductor to do this energy transformation. You could do the same thing also with capacitors, but if you want to make it with high efficiency, you need a current source to take your energy from, because otherwise you always charge the capacitor from a constant voltage, and initially the voltage across the capacitor is 0, so you're dissipating half of the energy, as you point out, in the wiring resistance or switch or whatnot. Okay? So that's a good point. Okay, so we're going to look at the power brick, and I looked on the web for a picture for a power brick, and this is what I found. So what we are interested in, of course, is what is inside this box, not the beautiful case. Okay. So here is a circuit that does this. So what does what? Well, we start with the 110 volts. Okay, that's what comes out of an outlet, more or less. Let's forget about the details there. And what we really want is 10 volts. Right? Most cell phones, if you plug them directly into 110 volts, well, they will be toast. All right, so the way we're going to do that is, well, we're going to use this circuit, and we will have to spend a little bit of time to understand it. But anyways, it's got a switch, and that switch opens and closes something like that. With a pattern like that. Okay? And of course, we can set the times when it opens and when it closes independently, and we make them always the same. Okay? So that's just how this circuit operates. Okay? Now, there is one more element in this circuit that we haven't talked about, and that's the diode. There is also an inductor in here. We've talked some about those, and there is the load, right? The load could be, of course, a resistor, but your cell phone isn't just a resistor, so I put the more generic symbol there. All right? So this is what we want to charge, and so now again, this extra element that we have, it's called a diode, and an ideal diode does the following thing. If the current goes in the direction of this little triangle here that we see in the symbol for the diode, if the current goes in that direction, then it's a short circuit. If the current goes in the other direction, it's an open circuit. So, with that, can we construct now the IV characteristics for this? So, if the current tries to go in the direction ID, then this voltage voltage VD is positive. The current is going in the direction of the arrow, and the thing is a short circuit. How do I draw this characteristic? Yes.
It starts like from 0, then it goes exponential.
No, it doesn't go exponential. A short circuit. We talked about short circuits for a long time, right? There were no exponentials. Huh? Yeah, a short circuit is just a wire, right? So, what's the voltage here? 0 volts, right? What's the current here? Doesn't matter. Okay? All right? It's a short circuit. So that would be question 5 on a midterm exam. Okay? All right? So now the voltage, actually, this voltage here is less than 0. So the current wants to go the other way. The thing is an open circuit. How do I complete the diagram? Current will be 0, right? Okay? Yeah, if I think about it, good question 5, maybe next year. Don't tell them. Okay, so now the way this circuit again operates, it's got this switch here, and the switch is closed for some time, T1, and then it is open for some time, T2, and then the whole thing repeats. Okay? So how do we analyze such a circuit? Well, we figure out what's going on when the switch is closed, and then afterwards, when we are done with that and we really understood that, then and only then do we go on to the situation when the switch is open, because if we mix the two, we confuse ourselves and we never get the answer. Okay? So the switch is closed, and I redraw the circuit here. Where is the switch? It's just a short circuit now, right? Okay, so now we have to figure out what's really going on in the circuit, and let's look first at this new element, the diode. What is this diode doing? So what actually was Vs? 110 volts, right? So Vs is 110 volts. So what is this voltage here? It's 110 volts. In which direction is the current trying to go? Well, this way, right? Can current flow in that direction through the diode? No. So this diode does nothing here. It acts like an open circuit, yes.
What does the value of the parameter D1 indicate? Is it just the
It's not a parameter, it's just the name. Exactly, just the name. There are somewhat different.
There actually is a parameter for diode.
Yeah, there are many parameters, right? But the ideal diode is just like this. In reality, diodes look like this, and then exactly how this looks like, this many parameters. But for us, it's good enough, the ideal diode, yes?
Why does the current go that way? Just because the voltage...
Yeah, it's a passive element, so the current wants to flow in the direction of the voltage, and it's a diode there, and the diode says, stop. It's like a one-way street, right? Yeah, check valve. Yeah. Okay, so this diode's not doing anything. It's like an open circuit, so I redraw the thing, and I recommend that you redraw the thing also if you're in such a situation, so that's what we end up with. So now the circuit is a lot simpler. Okay? Now we are gonna we could replace x1 with a resistor or something like that, and we have differential equations to solve and so on. We can do yet another thing. You remember for math, sometimes proofs work that you assume that the answer is correct, and then you somehow show that you don't get the inconsistency. Well, we do something a little bit similar here. We want, this is 110 volts, right? But if our circuit works all right, then this voltage here is going to be 10 volts. Your cell phone is not going to work if you give it 10 volts for a little bit, and then it's 0, and then it's 50, and whatnot, and so it's not going to work, right? So if this circuit has any chance of being useful to operate your cell phone, the voltage here better be 10 volts always. Maybe it has a little bit of a ripple up and down, but, not a whole lot, okay? Okay, so let's assume that the voltage here was 10 volts. What's the voltage across the inductor in that case? 100 volts, right? What's the current through the inductor? What is it doing? The current through the inductor as a function of time increases. Okay? And we know now how to calculate the rate of increase. Okay? That's why I made these examples, these trivial examples. Okay? So this is the current through the inductor. And we have a certain time, let me put it like this, a certain time, t1, during which, this is t1, during which the switch is closed. And so during that time, the current is going to increase by a delta I. And you can figure that out now. That's going to be equal to Vs minus V out, the 100 volts, divided by L1 times T1. Okay? That's the amount of the amount by which the current in the inductor increases. Where does it start from? Well, the very first time when you turn on this circuit, then of course it will start from 0. But after a while, it will not be 0 anymore, and it will start from a value that is not 0. Okay? All right. So that's what happens when the switch is closed. So now let's look at when the switch is open, and now it's trivial. We certainly can get rid of this part here. What is the diode doing? Well, here we have 10 volts. We perhaps have some voltage across the inductor, but actually, what is the current in the inductor? It's greater than 0 anyways, right? So there is a current that's flowing in this direction. What is the diode behaving like? Exactly, it's behaving like a short circuit. So how do I redraw the thing? Yeah. Okay, so that's what we have here, right? Now we have exactly the same situation again. This voltage it's going to vary a little bit up and down, but if it goes up and down by 100 millivolts or so, we're not going to get now into deep differential equations, right? We're solving it simply to understand how it's working and how to design it, not to do mathematical exercises. Yes?
How do you know the inductance had the positive voltage before?
Actually, I didn't really. I shouldn't have said that. This doesn't really matter. The point is that the inductor has a current that's flowing in this direction. The inductor current, is it going to change? Well, yes, but not instantaneously, right? So at least for a moment, that inductor current is going to be the same. It's still going in the same direction. And the diode needs to carry that current. There is no other place where it can go. And consequently, the diode must be conducting. And because it's an ideal diode, it then acts like a short. Okay? So, here we have exactly the same thing now. We have the voltage across our inductor is now minus 10 volts, and consequently the current is going to do the current in the inductor from wherever it was, it's going to decrease at the rate that is equal to minus 10 volts over L1, and this delta I is going to be equal to this times T2, the time T2 over which we run this thing. Okay? All right, so apparently that's what's happening. When the switch is closed, then what happens? The current increases, right? When the switch is open, the current decreases. When the switch is closed, it increases again, and so on. The current does a zigzag like that. Yes?
When the switch is closed, the voltage across the inductor is 100 volts, and when it's open, then it's only 10 volts, or negative 10. So
Right.
we have to open and close the switch, or keep the switch open more than it's closed to balance out the current.
That's absolutely correct. Absolutely correct. Yes. Of course, the ink. So actually, I thought while I drew this, I thought I could have drawn this a little bit better. And so let me do this. We close it for a short time. We open it for a longer time. We close it for a short time. Something like that. Exactly what you said. It increases very quickly. Why? Because the voltage is very high, like 100 volts. Then it decreases very slowly. Well, because we have only minus 10 volts. Then it goes up fast again. Does this. Thanks a lot. That's exactly the right insight that we need in order to understand what. How are we going to set the voltage V out? Well, we said we want it to be 10 volts, but why? Why is it 10 volts? Well, if we make this time here longer, is the voltage V out going to increase or is it going to decrease? Then it's going to decrease, right? And if we make this shorter, then the voltage V out is going to increase. So apparently, the voltage V out is set by the ratio of T1 and T2. By ratio of these two numbers. Okay? And of course, it's very easy to adjust those, which is precisely the reason why if you buy a power brick, this circuit is inside, right? And if you plug it in the US, then you get 110 volts, and it uses one ratio of T1 and T2. If you plug it in Europe, you get 220 volts, and then it just changes that ratio, and in the end, we still get 10 volts. Same circuit. Okay? Yes? No, it will go down like this if the voltage across the inductor is constant, right? Which is an assumption that we still have to make sure that it's true. Then the voltage goes linear down. So, which is precisely the reason why I chose this as something that I could explain you what inductors are doing, because there isn't a lot of complicated math here. There are not even any exponentials. But it's doing something really interesting. Something that you take for granted, but heck, you know, you're electrical engineers. Maybe a good idea if you have an idea what's going on inside. All right. So now we can we actually can solve the delta the delta I1 is equal to this times T1. And that must be equal to the delta I2 times T2. And out of this, we get V out over Vs equals T1 over T1 plus T2. Okay, so just what we said, what we understood qualitatively, the math also tells us that we set the output voltage by simply changing the ratio between T1 and T2. All right, so yeah, there is a little bit more. Maybe we'll do that next time. Okay. All right, so again, please, these simple examples that I've given you, please make sure that you can do them. Make sure that everything up to slide 30 or so in this lecture that you know, that you understand that. And if you don't, then please come and ask. It's interesting stuff. You may as well try to understand it. Thank you.